Hello class, I thought I would develop a video about Chapter 8. I noticed I didn't have a comprehensive video of Chapter 8 in my YouTube videos. So Chapter 8 and 9, we're focused on chemical reactions. Chapter 8, we're going to start with balanced chemical equations, and then we'll get into combustion analysis, which is a good precursor to stoichiometry. I assume most of you have had stoichiometry, which is where you determine how many grams of product will be formed from a certain number of grams of reactant. The combustion analysis, though, that may be new. It's a way to introduce multiple ratios and the relationship between molecular formula and empirical formula. So that may be new to some of you. Once we get into stoichiometry, we will then talk about limiting reactant, and we'll talk about actual yield, theoretical yield, percent yield, and hopefully that corresponds to a lab that you're doing in Chem 175 on stoichiometry. So that's the goal. That's what we're looking for. And then Chapter 9, we're going to talk about types of chemical reactions like precipitation reactions or acid-base reactions or oxidation reduction reactions, also called redox reactions. These are the chemical reactions that are most prevalent and are important in other classes besides chemistry. So when you're looking at a chapter, always look at this page. This slide tells you what you're supposed to accomplish. Now, I can tell you I do not lecture on section 8.5. I do want you to read it. I do want you to understand it. It is mostly descriptive chemistry, and all I would be doing is parroting back what's in the book. And so my lecture will cover sections 8.1, 8.2, 8.3, and 8.4. And we'll see where we're going to get as far as that goes in this lecture. Today, I lectured in class and we got up to section 8.4. So I may stop this lecture at 8.4 as well if I feel like this video is running too long. So again, chemical equations. It's important that you can write a balanced chemical equation, because if you can't do that, you can't do the rest of this. So it's important, and I think most of you have had balancing chemical equations. I'll talk about my method of solving or balancing a chemical equation. You may choose a different method. I think you choose the method that works best for you to ensure that you have the same number of atoms of each element on both sides of the periodic table. Of the chemical reaction symbol. And then combustion analysis, again, that's probably a new topic. If it isn't, you've had a really good chemistry background. But this is how we determine empirical and molecular formula of a compound. And then we'll get into stoichiometry, section 8.3. So a chemical equation, what you know is that there has to be the breaking of bonds and the formation of new bonds, and those new bonds form a new compound or a new element. So in this case, we have ammonia, and ammonia is NH3. And here's something I'm going to tell you. If you haven't got your naming down and your polyatomic ions down, it's going to ding you in this chapter and the next chapter especially. So if you cannot tell me that's ammonia and this is hydrogen chloride, and you don't know the formulas for those, then you need to go back and review that. There's no getting around it. That's one of the hurdles in Chem 170 is being able to identify a compound and go, oh yeah, that's ammonium chloride. This is the ammonium ion. It's a polyatomic ion with a positive charge. And then chloride, I know, being in group 17 forms a -1 ion. So we've gone from molecular compounds on the left-hand side to an ionic compound on the right-hand side. So those substances that are on the left-hand side of the chemical yield sign, that's what this is called, are called the reactants. And the substance on the left-hand side, or on the right-hand side of the chemical yield sign, is called the product. So again, you got to speak the language of a chemist, and we expect you to say reactants, products, chemical yield sign, and overall this is called a chemical equation because it's not a physical process. We are seeing new substances formed from breaking of bonds and new bonds forming. So we need to think about those things when we're talking about a balanced chemical equation. So when we talk about chapter 8, it really goes back to chapter 1, which Dalton said matter cannot be created or destroyed in a chemical reaction. So what we look for in a balanced chemical equation, if you say I have 1 mole of nitrogen here on the reactant side, I better have 1 mole of nitrogen on the product side. And then I've got 3 moles and 1 mole of hydrogen for a total of 4 moles. And so I have 4 moles of hydrogen on both sides and I have 1 mole of chlorine on both sides, or the chloride ion. So that's why, Dalton sets the foundation for chemistry by saying nothing disappears, nothing vanishes, all matter has to be accounted for. And so that's why balanced chemical equations work. The other thing, you need to be able to label what the substance, what phase of matter it's in. And we have 4 choices here: solid, liquid, gas, and aqueous. So you say, well, how am I supposed to know what these are? Well, if it's covalent and you had to guess, you would guess that it's a gas, because it's not until we get into strong intermolecular forces like hydrogen bonding with water that we get a liquid. So if it's not massive and it's covalently bonded and it's not hydrogen bonded, I think gas would be your best guess. I would expect most people to know that ammonia is a gas and not a liquid at this point. And then hydrogen chloride, if we say that's the name, that indicates it's a gas, because the other choice is bubble hydrogen chloride in water and becomes hydrochloric acid, so then it would be aqueous. And then ionic compounds, I would generally guess those are going to be solids. Just think about it: table salt, NaCl, calcium carbonate, sodium phosphate. All of those things are ionic compounds and they are solids at room temperature. So again, we have sulfur trioxide. Again, covalent molecular compound, would assume it's a gas, especially because it's a non-polar molecule. So you can see all this stuff we've been talking about this semester is starting to come into a summary so that you can look at sulfur trioxide and go, yeah, it's a trigonal planar molecule. Yes, it has polar bonds, but overall the molecule is nonpolar. That's what we learned in the last chapters on that last test. And so that's what we need here. And then we know water's polar, that it's a bent geometry, and that when we bubble sulfur trioxide into water, we get an acid, and this is an oxyacid, and we would call that sulfuric acid. Remember how we did that? We said SO42 negative. SO42 negative is a polyatomic ion called the sulfate ion, and the sulfate ion says if the ion ends in 8, the acid ends in ick, 8 something icky, so this is sulfuric acid. So again, we've talked about that before, and now it's all starting to come into play because this is what we're doing chemistry for, right? For the most part, we want to make new substances. We want to combine reactants and see what the products are going to be. And so this chapter and the next chapter, you're actually going to see a lot of what we call wet chemistry. So when we look at a reaction, you can interpret this 2 ways. You can say a molecule of hydrogen reacts with a molecule of oxygen to form a molecule of water. You could also say that 1 mole of hydrogen reacts with 1 mole of oxygen to form 1 mole of water. And the reason why we're generally going to lean towards moles is because moles is a quantity that we can see, that we can manipulate. A mole of water, we've calculated its molar mass before. We know that it weighs 18.02 grams per mole. If we were dealing with an individual molecule of water, it'd be 18.02 atomic mass units. And we're not going to be working with things that small in general chemistry. Yeah, it's important to be able to calculate it, to be able to call that a molecular mass. That's important. But when we're working in the lab, we're generally working in gram and molar quantities. So we know that this equation, this chemical equation, we know it's a chemical equation because new substances are being formed. This is violating the conservation of mass. That you have two hydrogens on both sides of the chemical yield sign, but you'll have two oxygen here, and you'll have one oxygen here. So that's a violation of Dalton's theories that he posted, that law of conservation of mass, which says matter cannot be created or destroyed in chemical reaction. So to balance this out, we add a stoichiometric coefficient. I do want you to know this word, stoichiometric coefficient. We got to speak the language. So stoichiometric coefficient is what these numbers are here, and there's actually three of them here. The stoichiometric coefficient in front of the hydrogen is 2. So what we're saying here is either 2 molecules of hydrogen or 2 moles of hydrogen react with 1 mole of oxygen, and we form 2 moles of water. Or you can think of it as 2 molecules of hydrogen react with 1 molecule of oxygen and form 2 molecules of water. Either way you want to think of it. But what you notice is no matter is being destroyed. There's my 2 oxygen from the reactant side. These 2 hydrogen go here, and those 2 hydrogen go there. So that's a balanced chemical equation. Notice the phases of matter, it's important, and that those phases are not subscripted. They are they're not like a 2 subscript here or 2 here or 2 here. They are as in the base. That's, I guess, the best way to say base. Okay, so matter cannot be created or destroyed. We have to balance a chemical equation. Yes, these substances are determined by the chemical reaction. Hydrogen and oxygen do react together and form water, and we know what the reasoning behind that is. We know that hydrogen is bonded to another hydrogen. It's a nonpolar molecule. Both hydrogens feel like they have 2 electrons, so they have a full outer shell of 2, which is fine for the first period. They're isoelectronic with helium. These are the things we've learned this semester. And the same thing here, we know that the Lewis structure for water looks like this. And we know that this is AX2E2, and the electron domain geometry is tetrahedral, and that's why the molecular geometry is bent. And we know that these bonds are polar because oxygen's more electronegative than hydrogen. So the oxygen is partially negative here, and the hydrogens are partially positive here. And we know water has different chemical and physical properties than hydrogen and oxygen. So all the stuff we've learned this semester is coming to bear here in chapter 8 and 9. So balancing chemical equations, they do give you some rules here. It is a trial and error approach, bottom line, and you have to come up with your method of how you're going to balance the equation. I'll talk about my method, and then you can decide if you want to do that. But the whole thing, the one that does help a lot is treat the polyatomic ions, if they appear on both sides, as a unit. Like if you have phosphate on one side and it's still phosphate on the other side of the chemical yield sign, treat it as a whole unit. Do not break that down into 1 phosphorus and 4 oxygen. It'll make it much easier to balance your equation if you do that. All right? So that's the big rule for me. But again, I'll show you how I generally balance a chemical equation. So what I do is I want to hone in on this substance not because it's a reactant, but because this carbon is going to affect carbon dioxide, how much carbon dioxide is going to be formed, and this hydrogen is going to affect how much water is going to be formed. So when I see a substance that has multiple elements in it, that's going to be the first thing I try to balance. The last something like a pure that's just an element, like this oxygen. So oxygen ends up being that, and water are some of the last things I always balance in a chemical equation. Why the oxygen? Because if I change the coefficient in front of the oxygen, it just changes oxygen, doesn't change the carbon or the hydrogen. So that's why I would leave off balancing the oxygen to the end. So right off the bat, I know I need a coefficient of 3 in front of the carbon dioxide. Why? Because I've got 3 carbons bonded to 8 hydrogen here. So I got 3 carbons on both sides of the chemical yield sign. And I know that I've got 8 hydrogen here, so I need a coefficient of 4 in front of the water. So that gives me 4 times 2. I got 8 hydrogen on the product side. Now I'm ready to balance the oxygen. So I go 3 times 2, that would be 6 oxygen. And then I got a coefficient of 2 here. So 2 times 1, I have 2 oxygen. Oops, did I? No, this is a 4. Yeah, I knew that didn't look right. 4 times 2, 8 oxygen. So then I have 6 plus 8 is 14 oxygen. And so I need to put, what have I done here? Oh, this is just 4, 4 oxygen. All right. Well, I'll figure 10 oxygen. All right. So then I need to put, this is my only place oxygen's located, so 5 oxygen here. All right. So that gives me 10 on both sides. So now you're like, yeah, I'm confused. Okay. So sometimes that happens at the end of a problem. You got to center and think about it. So when you think you've got these right, a 5 in front of the oxygen, a 3 in front of the carbon, you go, let's go through this again. You got a 3 here, you got to have a 3 carbon here, so you put a coefficient of 3 in front of the CO2. You got 8 hydrogen here. This is the only place hydrogen's located. You got 2 of them, so you got to put a 4 there. And then, 3 times 2 is 6, and 4 times 1 is 4. That gives me 10 oxygen. And then I need to put a 5 in front of the O2 to give me 10 on that side. So just double check your work. That's the bottom line. In the end, once you think you have it done, go back and check to make sure each element, there's the same number of each element on both sides of the chemical yield sign. So here's where I see students struggle the most. And this is going to happen in this chapter and the next one. They just say barium hydroxide reacts with perchloric acid to produce barium perchlorate and water. Now, a student that hasn't learned or memorized the polyatomic ions or the names of the elements, they're going to have a hard time with this because you're going to have to know that barium is at a group 2. It forms a 2 positive ion. Hydroxide is a -1 polyatomic ion, and that's why you got to have 2 of these polyatomic ions. That's why you have the parentheses and the 2 subscripted. Perchloric acid, you're going to have to know, this is what we did when we did naming. We said you memorize that this is the perchlorate ion, and you're going to add a hydrogen to that, and that's going to give you HClO4, and I ate something icky, so that becomes perchloric acid. So there's my chemical formula for perchloric acid. Then it says barium chlorate, and knowing chlorate's a -1 ion and barium's a 2 positive ion, that's why there's a 2 here. And then the hydrogen's going to react with the hydroxide to form water here. So we talked about double replacement reactions in the past. So barium goes with the chlorate, the hydrogen goes with the hydroxide, and that's how we know what the 2 products are going to be: barium chlorate and water. So again, if you said something like barium dichlorate or something like that, that means you're confusing molecular compound naming and ionic compound naming. This is an ionic compound. This is a barium 2 positive ion with a chlorine negative ion. So all that comes into play. That's why we're getting to the end of the semester. All of this starts to become real, and we have to start integrating it. And this is what you need in order to be successful in Chem 180. So now let's balance the equation. So I would probably look at this substance because it's got the barium and the chlorate. So the chlorate doesn't change. So that's what I mean. If it doesn't change from one side to the other, balance it as a whole. So you got two of them on the product side. So let's put a 2 here in front of the perchloric acid. That gives me 2 perchlorates on both sides. And then the barium, we need 1 barium. We got 1 barium here. That looks good. So we're fine there. So then the last thing we have to do is we got to get these waters. So like I said, oxygen or water is generally the last thing you balance. So you've got 2 times 1 and then 2 times 1. You got 4 hydrogen total on the reactant side. So that means you're going to need to put a 2 on the product side in front of the water. Coefficient of 2 in front of the water. Now, before you say you're done, I think the big thing here, let's just check the oxygen to make sure. So we got 2 times 1, that's 2 oxygen. We've got 2 times 4, that's 8 oxygen. So that's 10 oxygen. And then over here, 2 times 4, 8 oxygen, and 2 oxygen, 2 times 1, 2 oxygen, 10 oxygen. So I'm confident my answer is correct, and I'm ready to move on. But that's what you have to do. It's back and forth, kind of keeping track of it. If you get lost in the back and forth, then you're going to have to start writing it down like they show in these examples. So if you want to do that, if you want to, you really have trouble balancing chemical equations, you're going to have to do it through a series of systematic steps that you want to write down on paper. Right? In the end, it's worth doing a check just to make sure everything's correct. All right, let's look at another problem. So we got butyric acid, also known as butanoic acid. This is what makes butter taste like butter. So 1869, they isolated butyric acid in butter, in rancid butter. Rancid butter is after the butter goes bad. It's got a real sour taste to it. It really stinks. And I don't expect you to know the chemical formula for butyric acid or butanoic acid. But I expect you to be able to read this problem and write a balanced chemical equation. So it says write a balanced equation for the metabolism, and you're going, what does that mean? And for butyric acid. Well, I don't expect to know what metabolism is, but it is the breakdown of the butyric acid. So they tell you, they say it reacts with oxygen and it produces carbon dioxide and water. So now you have all the components to write your equation. You have the butyric acid, that's a reactant. You have oxygen, which is a reactant, which produces carbon dioxide, which is a product, and water, which is a product. I do want you to know anytime you combine something with carbon and hydrogen and it reacts with pure oxygen, your 2 products will always be CO2 and water. All right, a carbon hydrogen based compound reacting with oxygen, that's called combustion generally, but we can also describe it as a metabolism. So combustion or metabolism. Combustion specifically means oxygen. Metabolism is generally oxygen. So knowing this, knowing what you've read in this problem, you can write a balanced chemical equation. So you may want to stop the video and see if you can do it. And if you can, you're in great shape. So here's what it looks like. Butyric acid plus oxygen, that's my reactants, and my products are CO2 and water. I got the phases of matter here, so make sure you put those in. So the first thing I'm going to do is this is what I'm going to focus on because it's got carbon, hydrogen, and oxygen. So I'm going to put a 4 in front of the carbon. I'm going to put a 4 in front of the water so that I have 8 hydrogen on both sides. And then the oxygen, I'm going to go, okay, 4 times 2 is 8 oxygen here. And I'm going to say 4 times 1 is 4 oxygen here. So that's 12 oxygen. I've got 2 here, so I need a 5 here to give me 10 oxygen plus the 2 oxygen here to give me 12 oxygen on both sides. Now, sometimes I see students put a 6 here instead of a 5, and it's because I didn't look at these 2 here. And hopefully when you go to double check your work, you would catch that mistake. But that's a common mistake. It's okay if you made that mistake, but just know oxygen occurs in 2 different places, and that does happen in chemical reactions. You may have an element in more than one compound on the reactant side, and you'll have to add those up. All right. So in the end, though, check your work. 4 carbon, 8 hydrogen, 8 hydrogen, and then 2 plus 10, 12 oxygen. 4 times 2 is 8. 4 times 1 is 4. 8 plus 4 is 12. And you know you solved the problem correctly. All right. It's important to understand the pattern of a chemical reaction. Like, look at a chemical reaction and tell me what type of reaction is happening. I know a lot of times students skip over this. They don't think it's that important, but it is such a clue to tell you what's going on. So when I see ammonia react with hydrogen chloride and it only forms ammonium chloride, I know that's a combination reaction. I'm reducing the amount of substances on the product side. And then the opposite, when I start with one substance and I end up with multiple substances on the product side, that tells me that's a decomposition reaction. When I start with one substance and end up with lots of substances. One thing here to note is this little delta here means heat. And so don't think it was just change, that if you put a delta sign over the chemical yield symbol, that tells a person you've applied heat for this reaction to happen. And then the last one, we've already talked about, any carbon-hydrogen compound burned in pure oxygen, we call that a combustion reaction. You should always get CO2 gas and H2O or water as a liquid. All right? So know what type of reaction you're dealing with. So at this point, I would expect you to be able to look at these reactions and tell me that this is a combination reaction, this is a combustion reaction, and this is a decomposition reaction. All right? So look at the previous slide, look at this slide, but you want to be able to sight recognize what type of reaction you're dealing with. And you say, why do I need to know this? I think it becomes more apparent in the next chapter because we'll talk about signal replacement, double replacement, reactions, and disproportionation reactions. And I think it's important that you can identify the type of reaction. It helps you solve more complex problems later. All right, a lot of times people skip over this section, and I have too. But there is some utility. There's some reason to follow this section. And so I want to talk about how we determine, like let's say I have a sugar, and we're going to see a problem like this, but I don't know what the mole to mole ratio of carbon to hydrogen to oxygen is in the sugar. What's the actual value of X, Y, and Z here? I gave an example in class today. This, along with mass spectrometry, is how we determine we determine the make and model of a car that's involved in a hit and run accident. So when someone hits a person with a car, the paint generally breaks off of the car. So there'll be paint chips at the accident scene. And the detective will scoop those chips up into a bag and they send them to the state police. And we use an instrument similar to this one, and we can determine the amount of carbon, hydrogen, oxygen, and other components with mass spectroscopy of the makeup of that paint. And then we have catalogs online that will tell us the make and model and the approximate dates that car was made. So we'll know that it's a Chevy Impala, that it was red in color, and this paint was used from February of 2020 to June of 2020. So it gives us all that information, and then we can either look at cell phone pings, or cell tower pings. So we know now we have an idea of the identification of the cell phone and the make and model of the car and the year, and we can correlate that with the registration number and the VIN number, and we got a pretty good idea of who has hit the person. We're not exact because somebody else could have been driving, but we got a great place to start. We can also look at cameras, see what cameras were in the vicinity when that happened, see the cars that were in the vicinity, and generally that matches up pretty good as well. Like we can see, oh, there's an Impala in there. It's red. So, and sometimes we can get the license plate off the car from that. So this is what we're doing here is we take a sample that we don't know the amount of carbon, hydrogen, and oxygen. We heat it up in the furnace and we pass pure oxygen through here. And what happens is again, hydrocarbon burns in pure oxygen. The two products are water and carbon dioxide. So I measure, I weigh these discs before we start the process, and then I'll weigh them after the sample has completely been combusted or burned, and that'll tell me how much water I can take. The water plus the disc, subtract off the mass of the disc, and I'll know exactly how much water I collected. Same thing here. Collect the CO2 plus the disc, subtract off the mass of the disc. I know exactly how much CO2 was collected. So from this, I can tell you how much hydrogen was in the sample. I can tell you how much carbon's in the sample. If I combine these two things, and I know how much carbon and hydrogen is in the sample, if I subtract that from the initial sample mass, let's say this was 20 grams, I can then tell you how much oxygen was in the sample. So I can tell you how many grams of oxygen, how many grams of hydrogen or either water or hydrogen that were in the compound, and how many grams of carbon. So let me show you how this works as a math problem. So here we have sugar. So our initial sample that we placed in the instrument is 18.8 grams. I don't know what the moles of carbon, hydrogen, and oxygen are in this sugar, but I do know I collected 27.6 grams of carbon dioxide and 11.3 grams of H2O on those discs. So I can take the 27.6 grams of carbon dioxide, I can use the molar mass, and this is what's really important. Anytime you want to go from grams to moles or moles to grams, it ought to be automatic to you at this point that you need the molar mass of that substance. So carbon weighs 12, oxygen weighs 16. 16 times 2 is 32 plus 12. That's where we get the 44.01. You get it from the periodic table. You get the molar masses of the elements. You multiply the molar masses of the elements by how many of that element you have. You total that up, and that's your molar mass. Now, you know you set this up right because the grams of carbon dioxide are going to cancel out. You're going to be left with moles of CO2. Then, looking at CO2, for every 1 mole of CO2, you had to have 1 mole of carbon. For every 1 mole of this, you have 1 mole of carbon. This is called a mole-to-mole ratio. This is the most missed part of the problem. It's easy, but students, for some reason, they get a mental block and go, how do I get from here moles of CO2 to grams of carbon? Well, you have to look at the relationship between CO2 and carbon, and it's 1 to 1. So that's what we have here. The moles of carbon dioxide cancel out. The moles of carbon, we can get that into grams by using the molar mass of the carbon, which we get from the periodic table. And so the moles of carbon cancel out, and you're left with grams of carbon. So now I know in my sample that I burned that there were 7.53 grams of carbon. Do the same thing for the water. This is how much water was collected on the disk. We weigh the disk before and after the reaction. That tells us how much water was collected. We use the molar mass of not carbon. It's the molar mass of water. There's a typo here. 1 mole of water weighs 18.01 grams. So 11.3 divided by 18.01, the grams of water cancel out. We're left with moles of water. Now watch this one. For every 1 mole of water, there are 2 moles of hydrogen, because it's a 1 to 2 ratio here. So now the moles of water cancel out. We're left with moles of hydrogen. And I can get moles of hydrogen into grams of hydrogen knowing the molar mass of the hydrogen, which I get from the periodic table. So the moles of hydrogen cancel out. We're left with grams of hydrogen. This is how many grams of hydrogen were in our compound. So here's the tricky part. Most students get through this. The ones who get through this part, the next thing is what's the mass of the oxygen? So you take the entire mass of the glucose, which was given in the problem, and then you subtract off, and this is what I find most students fail to do. You got to do a parenthesis here. Parenthesis, add your carbon and your hydrogen that you just calculated, sum those together and get a number here before you subtract from 18.8. So if you have 7.53 and you add to that to 1.26, you get 8.79, all right? 8.79, which when we subtract 18.8 minus 8.79 to the tens place, we get 10.0 grams of oxygen. So now we know the grams of carbon, hydrogen, and oxygen in the compound. So don't forget this step. A lot of students miss this step, and it's easy once you've done most of the work. You just got to go one extra step and take the total mass minus the mass of the carbon and the hydrogen, and you get the mass of the oxygen. Now, the molar mass of carbon is 12. The molar mass of hydrogen is 1 gram per mole, and the molar mass of oxygen is just singlet oxygen is 16 grams per mole. When it comes to chemical reactions, it's not about mass reacting with mass. It's about, is there an atom reacting with another atom that's creating the bond? So each one of these elements weighs a different amount per mole, different amount per atom. So what we need to do is convert these masses into moles. So that's what we're going to do on the next slide. We're going to take the mass of carbon that was in the compound and use the molar mass of carbon to determine how many moles of carbon was in the compound. Do the same thing for the hydrogen. This is the mass of hydrogen we determined was in the compound. Use the molar mass of the hydrogen to convert that to moles. Do the same thing for oxygen. Now, we know the ratio of carbon to hydrogen to oxygen has to be whole numbers. Again, that's going back to Dalton. Dalton says that atoms combine in whole numbers. Okay? So these aren't whole numbers. So students that haven't had much chemistry, they're just going to say, well, this 0.6 rounds up to a 1, and this 1.25 rounds down to a 1, and 0.626 rounds up to 1. That's not the way it works. This is how much carbon you have. This is how much hydrogen you have. This is how much oxygen you have. What you do is you divide by the smallest of these moles. So 0.626 is smaller than 1.25 or 0.627. So we divide each of the moles of each of the elements by 6.626. When we do that, we get a 1 to 2 to 1 ratio. We get this. This is going to be 1. 6.627 divided by 0.626 is 1. 1.25 divided by 0.626 is 2. This is called the empirical formula. The empirical formula is the simplest whole number ratio between elements in a compound. Now, we've talked about empirical formula before. When we said my classic example of empirical formula is when you have 10, 4 positive, and we're going to combine that with sulfur 2 negative, and if you do the crisscross method, you get a 2 here and a 4 here, and that's not the correct formula because both things can be divided by 2, and you get SNO2. That's why I like to just say, what do both numbers go into? 4, you need 110 and 2 oxygen. That's the simplest whole number ratio. Ionic compounds are written in their simplest whole number ratio, which is called the empirical formula. But what we've done here is calculate the empirical formula for a covalent or molecular compound. So you say, why would I ever do this? Well, if these are sugars, that's a telltale sign that you have a sugar, that the carbon to hydrogen to oxygen ratio is 1 to 2 to 1. So whether I'm talking about maltose, dextrose, glucose, sucrose, I should see a carbon to hydrogen to oxygen ratio of 1 to 2 to 1. And so instead of writing all the sugars down, I may say I'm dealing with a group of sugars with the empirical formula CH2O. The main thing here is that these have to come out to be whole numbers. If you get something after you divide through, it comes out to something like 1.5, and this is 1. Don't round this. This is an improper fraction. This is 1.5, which is 3 halves. And so you have nitrogen 3 halves and oxygen. And then you'd multiply the entire thing by 2, and you get N3O2. So that's going to happen sometimes. If you get like 1.25, 1.5, you get 1.67, 1.33, 1.75. Those are all fractional amounts that you're going to have to make an improper fraction and then find out whatever's in the denominator, you're going to have to multiply that number through the whole series of elements in the compound. All right. So once we get the empirical formula, a lot of times what we want to do is figure out what its molar mass is. So carbon's 12, hydrogen's 1. We got 2 of them, so that's 14. 14 plus the 16 for the oxygen is about 30 grams per mole. Okay? So that's the molar mass of the empirical formula of this substance. Now, if they gave us the molecular mass, they told us that, oh, no, it's molar mass. This is also called molar mass as well. But if they gave us the molecular mass or the molar mass of this sugar, and it was 180, then I could divide the 180 by the 30 that we just calculated for the molar mass of the empirical formula, and that gives me a multiplier, 6. So I would multiply 6 times the empirical formula, and I would get my final formula, which is called the molecular formula. And it would come out to be C6H12O6. 6 times 1 is 6. 6 times 2 is 12. 6 times 1 is 6. That's how we get this number here. So if you are given the molecular mass, you can divide it by the empirical mass, find out what the multiplier is, and multiply through on your empirical formula to determine the molecular formula. All right, I'll skip over this one. I'll let you try this one out. If you can do this one on your own, you're in pretty good shape. All right, so back to balancing chemical equations. This is a balanced chemical equation. We can see matter's not created or destroyed. There's one carbon here, there's one carbon there. There's a total of 4 oxygen, and there's a total of 4 oxygen on the product side. So it's balanced. So what's important here is these stoichiometric coefficients. And let me just say, sometimes on a multiple choice problem, they say, what is the sum of the stoichiometric coefficients for your balanced chemical equation? And the answer would be what? So stop the video, write down what the answer would be, and then start the video back. The answer is 5. All right? There is a 1 here. We don't write it. It's understood that there's a 1 here. If it's in the chemical equation, it's understood to be 1. So 2 plus 1 is 3, plus 2 here is 5. So don't make that mistake, because I know you know how to balance a chemical equation, and you're just not thinking about there is a 1 here in front of that oxygen, because it's not written. All right, so why are we doing this slide? Well, we're going to now do multiple ratios in a balanced chemical equation. Multiple ratios in a balanced chemical equation. You go, why do we do that? Because it's going to allow us to relate carbon monoxide to oxygen or CO2. Or we can relate oxygen to CO2. So we can get different relationships, just like we learned in chapter 1, that 1 kilogram is equal to 10 to the third grams. That's a relationship. We can say 2 moles of carbon monoxide is equal to 2 moles of carbon dioxide based on our chemical equation, this relationship and this relationship. Or we can say 1 mole of oxygen is equivalent to 2 moles of carbon dioxide. So this is how we're going to use this. We're going to use our balanced chemical equation to begin the process of doing a stoichiometry problem. So here's how it works. They say consider the complete reaction of 3.82 moles of carbon monoxide to form CO2. So we're looking at this and this. How many moles of carbon dioxide would be produced? If I have 3.82 moles of carbon monoxide, how many moles of this will be produced? So I write down what's given, 3.82 moles of carbon monoxide, and then I look at my balanced chemical equation. I see a stoichiometric coefficient of 2 in front of the carbon monoxide, a stoichiometric coefficient of 2 in front of the carbon dioxide. My mole to mole ratio is going to be 2 moles of carbon monoxide in the denominator and 2 moles of carbon dioxide in the numerator. So you say, why'd you do that? Because I'm trying to change this to this. So I want the carbon monoxide to cancel out. That's how I know what goes in the denominator here. And I want to end up with carbon dioxide. That's what goes in the numerator. Do I know this relationship? Absolutely. For every 2 moles of carbon monoxide consumed, 2 moles of carbon dioxide are formed. So I know I've set it up right, and my final answer comes out to be 3.82 moles of carbon monoxide. And you say, well, that's the same number. Yeah, it is, because the ratio is 2 to 2, which is 1 to 1. Now, when you write it on your paper, you still say 2 to 2. Don't simplify this and say, well, it's 1 to 1. You can do that in your head if you want to, but you want to leave that as 2 over 2 so anybody looking at your work can follow where these 2's came from. I can see this 2 came from here, and I can see that 2 came from the stoichiometric coefficient in front of the carbon monoxide. So this is called, let me erase all that so we can clear that up a little bit. This is called your mole to mole ratio. Oops, let's go back. This is called your mole to mole ratio. Comes from your balanced chemical equation. If you don't have a balanced chemical equation, or you haven't written a correct chemical equation, you cannot do the stoichiometry. You cannot do the mole to mole ratio. All right, so then here's a common question. I'm paying for oxygen. How much oxygen do I need to consume all 3.82 moles of carbon monoxide. So I need to know the relationship between carbon monoxide and oxygen. So I write down what's given. I've got 3.82 moles of carbon monoxide that was given in the problem. Then I will look at the relationship between 2 moles of carbon monoxide is equivalent to 1 mole of oxygen. I'm trying to get rid of the carbon monoxide, so just like we did in chapter 1, we divide both sides by 2 moles of carbon monoxide. This side becomes 1. This tells me this is a true conversion factor, which is a mole-to-mole ratio. We know we set it up right because the moles of carbon monoxide cancel out. We're left with moles of oxygen. This is the stoichiometric equivalent of how much oxygen I need to consume 3.82 moles of carbon monoxide. Mole-to-mole ratio from the balanced chemical equation. All right, so they get more complex. In this problem, you have to know ammonia is NH3. You know that it's trigonal pyramidal, so that's why it's drawn like this. You know carbon dioxide is CO2. It's linear. I don't expect you to know urea, so they give you the chemical formula for urea, and I don't really expect you to be able to draw this structure. But I do expect you to be able to write water and know that it's bent, and it looks like that. So this equation's balanced. We got 2 nitrogen on the reactant side, 2 nitrogen on the product side, 2 times 1 there. We've got 1 carbon on both sides. We've got 6 hydrogen on both sides, and we have 2 oxygen on both sides. So the equation's balanced. And the question is, if I have 5.25 moles of ammonia, how much urea would be produced? So if I've got 5.25 moles of this, how many moles of urea is going to be produced? So I look at my balanced chemical equation. I see for every 2 moles, let's do it this way, 2 moles of ammonia is equivalent to 1 mole of urea. I'm just going to write a U. I'm running out of space there. So then knowing that equivalent from the balanced chemical equation, I can do a mole-to-mole ratio. So here's how many moles of ammonia I have. For every 2 moles of ammonia, 1 mole of urea is produced. I set this up so that the moles of ammonia cancel out, and I get moles of urea. So 2.63 moles of urea would be formed. And again, let me just say this. Everything we've been doing in this chapter, this is called theoretical yield. This is assuming 100% completion, and we just need the exact amount needed or to cause the reaction to happen, or here we're assuming 100% of this is going to be consumed and it's all converted to urea. These are theoretical calculations. In reality, probably not all the ammonia is converted to urea. Some of it's left as ammonia. And you'll learn about that in Chem 180 when we talk about entropy. All right, so that's easy. There it is, your mole-to-mole ratio. They're spending a lot of time on this because they know once you got the equation balanced, the next tricky part for students is coming up with that mole-to-mole ratio. Same thing for the second one. If we go back, it says determine the stoichiometric equivalent amount of carbon dioxide required to react with 5.25 moles of ammonia. So what I want to know is how much CO2, stoichiometric equivalent amount, how much CO2 do I need to consume all 5.25 moles of ammonia? So I need a relationship between ammonia and carbon monoxide. It's a 2-to-1 relationship. Let me erase that so you can see it. 2-to-1 relationship. Okay, so it's 2 here, 1 here. So again, you're going to write it as an equality. You're going to say, oh, that's 2 moles of ammonia is equivalent to 1 mole CO2. And since I have the moles of ammonia, I want to divide both sides by 2 moles of ammonia to create the conversion factor I need. Just like we did in chapter 1. This side becomes 1. This tells me this is a true conversion factor. It's just that we got a label for this now. It's called the mole to mole ratio. And there it is, 2 to 1, right there. You know you set it up right because the moles of ammonia cancel out. You're left with moles of CO2. And so there's your answer. The other thing here is make sure you watch your significant figures. If this has 3 and this does not determine your significant figures, you should have 3 in your final answer. All right, so this is about as hard as they get as far as your basic stoichiometry problem. I'm not talking about limiting reactant, that's probably the hardest, but this is your basic stoichiometry problem. What I mean by this is about as hard as they get is you start with a mass of a substance and you end with a mass of substance instead of just moles. And the reason why this is important is because when you're working in the lab, you're weighing things out in grams. You're not weighing things out in moles. Now, you may weigh out a molar quantity of something, but you'll know that if I've got a mole of water, it's 18.01 grams. That's what you're going to weigh out. So most of the time in real life, in the lab, we got to convert moles, grams to moles. Then we use moles to moles when we're looking at it in relation to our balanced chemical equation. That's where we get our mole to mole ratio. But at the end, we'd like to know how many grams of product is going to be formed. Not how many moles, but how many grams of product is going to be formed. So that's what this problem is. So out in the wild, wild west, you had a tooth that was aching. Yeah, you could just go in, they take a pair of pliers and just yank it out of your mouth, and very painful. But then we had fertilizer, ammonium nitrate, and if we heat this ammonium nitrate up, the gas that comes off of ammonium nitrate is dinitrogen monoxide, also called nitrous oxide, and we call that laughing gas, and then water. So they heat up some fertilizer, ammonium nitrate. Patient would breathe that in, kind of kill the pain, and then they'd yank your tooth out, and you pay extra for that because you didn't want to deal with the pain. So yes, you did. Oops, you did pay extra for that, and but that's okay. If you had the money, you did it that way. If you didn't, you either had somebody yank it out with a pair of pliers, or maybe you had your buddy knock it out. So, anyways, you need 10 grams of nitrous oxide to make this person feel good. So the question is, how many grams of ammonium nitrate do I need to heat up to get 10 grams of nitrous oxide? And again, there's our symbol there that talks about heat. So ammonium nitrate is our reactant. Our products are nitrous oxide or dinitrogen monoxide and water, but we're interested in the nitrous oxide. So you got to come up with your plan of action. So the first thing is nitrous oxide and ammonium nitrate weigh different amounts. So the first thing you'll have to do is convert the dinitrogen monoxide into moles of, I'll just say nitrous oxide. How about that? Once I get that, I can look at my stoichiometric coefficients and I can convert that to moles of ammonium nitrate. And then once I get moles of ammonium nitrate, I can use molar mass to convert that to grams of ammonium nitrate. So this is called the plan of action. Plan of action is super important. I don't care if it's chemistry or if you're with your advisor, you come up with a plan of action of what classes you need to take next semester. And somebody writes that down. You don't just do it in your head and that's it. Somebody writes down your classes, or you write them down and say, I need these classes next based on what I've taken, and I need these classes next so I can continue on with my degree. Or what we do in my office is a student's not doing well in class, they schedule an office hour with me, and we come up with a plan of action of how they're going to improve their grade in the class. Maybe they're not spending enough time reading the material and taking good notes. and watching the videos, and there's things I can look at how much time you're spending in Alex. We can look at your old exams and see what you've missed, and then talk about why you missed it. So we come up with a plan of action of how you're going to improve. Well, the same thing here. When you deal with a complex problem, you always write down your plan of action, your thought process of how you're going to solve the problem, and then you're going to do it. So from my plan of action, I see I need to convert the 10 grams of nitrous oxide into moles. And you go, oh yeah, if I need to convert grams to moles, I can easily do that. That's molar mass of nitrous oxide. When I see I got moles of nitrous oxide to moles of ammonium nitrate, I go, the only place I know that relationship is from my balanced chemical equation. For every 1 mole of nitrous oxide consumed, I need 1 mole of ammonium nitrate, mole to mole ratio. This is the most missed part of the problem right here. And then once I get moles of ammonium nitrate, yeah, I can convert that to grams using the molar mass of ammonium nitrate. So I think everybody gets really automatic about grams to moles and moles to grams using molar mass. So the new thing really is this mole to mole ratio. And again, where does the mole to mole ratio come from? It comes from your balanced chemical equation. So they broke it down into 3 steps. You could do this all one step if you want to. Maybe you've been taught that way, but they broke it down into 3. They took the 10 grams of nitrous oxide, used the molar mass of nitrous oxide to convert that to moles. Once they have the moles of nitrous oxide, they go to their balanced chemical equation, see that the stoichiometric ratio of nitrous oxide to ammonium nitrate is 1 to 1. So that's what allows you to convert from moles of nitrous oxide to moles of ammonium nitrate. And then once I have the moles of ammonium nitrate, I just need the molar mass of the ammonium nitrate to convert that to grams. All right? That's a stoichiometry problem. That's what we're looking for. Are they all this complex? No. Maybe all you have to do is change from moles of nitrous oxide to moles of ammonium nitrate. In that case, you'd only be doing step number 2. But because this one, you had grams of nitrous oxide, and you have to convert that to moles to relate it to the balanced chemical equation. And then at the end, they don't want the moles of ammonium nitrate. They want the actual grams of ammonium nitrate that you're actually going to burn. So you have to read the question carefully and determine how much or how far you're going to go. And that's why the plan of action is really important. Now, you could also determine how much water is going to be formed. I'm not going to go through these steps, but try that one on your own, and you should come up with this answer here. And if you don't, then you've made a mistake somewhere. There's some part of that plan of action you're missing. All right, that's where this video is going to stop. That's where I stopped today in class. And we'll pick up on limiting reactants in chapter 9 on the next meeting. Thank you.